Well, hello everyone. What we've got here is going to be a short video on solving some simple trig equations. So what we have, let's start with our first example, would be something like solve 2 cosine theta equals square root of 3, and all your solutions are in the range 0 to 2 pi. Well, we solve it pretty much the same way you solve typical equations. Dividing both sides by 2, we end up with the cosine of theta equals root 3 upon 2. What does that mean? Well, that means that we need to find a theta that has the value the inverse cosine of root 3 upon 2. A good way of looking at these type of questions is to find your unit circle and to look for the 2 examples in the range 0 to 2 pi at least, where the angle theta has an x-coordinate of root 3 upon 2. Now, since it's positive, we know that we should be looking in the first and fourth quadrant, and I believe the angles you get there are pi upon 6, that's in the first quadrant, and 11/6 pi, which is the one in the fourth quadrant. And that's pretty much what the solution would be if the question had simply been in this range here. But suppose they wanted the general solution, right? No restrictions on theta at all. They want the general solutions. So if they were looking at that situation, what you would probably just see is solve the equation 2 cosine theta equals root 3 and nothing else. So what we need to do here is that we need to realise, because it's important to generate these, that the period of the cosine function is 2 pi. What that means is that anytime you get an angle, if you add another 2 pi to that angle, you get one that also works. So you can imagine we have 2 solutions right now. But if we add 2 pi to them and then add another 2 pi or subtract 2 pi for eternity, then what we generate is this. Theta, a solution to that particular trig equation, is pi upon 6 plus the period times k. So pi upon 6 plus the period of the cosine function, which is 2 pi k, and an equivalent one for the second answer, which was 11/6 theta. If we move on and see what our second example looks like, we're going to solve a trig equation, 2 cosine x plus 3 equals 2, in the interval 0 to 2 pi again. We'll start off pretty similar process. Subtract 3 from both sides to get -1. Divide both sides by 2 to get -1/2. And that means that x will be the inverse cosine of -1/2. Right. So what we're looking for are 2 angles x in the unit circle that have an x-coordinate of -1/2. Now, since that's a negative number, we know we need to go and look at the second and third quadrants, and the ones that work, I believe, are 2/3 pi and 5/3 pi. Technically, in this question, it's x equals 2/3 and x equals 5/3. Now, what we do is we then look at, well, what would the result looks like if there was no restrictions? Well, use these 2 guys here, the 2/3 and the 5/3, as your building block, then add multiples of its period, multiples of 2 pi. So in this case here, since the cosine of x is 2 pi, it will generate the following solutions. X will be 2/3 pi plus 2 pi k, and then the other family of solutions, because technically there's an infinite number of them, you get from this fella here, where the angle x is equal to 5/3 pi plus a multiple of its period. Let's look at our next solution, our next question, we should say. Example 3. So we're trying to solve 2 sine theta plus 2 equals 0. Subtract root 2 from both sides, divide both sides by 2, and we are looking for some angles that have the property that they're equal to the inverse sine of negative root 2 over 2. Right, now that is negative, so I know that a sine function is only going to be negative when you look at the third and fourth quadrants. So let's see where we are going to look. So when is this going to happen? Well, it's going to happen when you're looking at the third quadrant and the fourth quadrant. Now, the two angles that do that are in the third quadrant 5 quarters, and when you go to the fourth quadrant it works at 7 quarters. So our two solutions in the range 0 to 2 pi are these two. Suppose there was no restrictions then. Well, you take your answers, your first one is 5 quarters pi, and you just do multiples of 2 pi, which is that one. And then to get the other one, you take 7 quarters pi and do a similar kind of thing. So what we'd have is 7 quarters pi plus a multiple of 2 pi. 2 pi k means a multiple. It means 2 pi times 1. Well, that's 2 pi. 2 pi times 2 is 4 pi. Times 10 would be 20 pi. And k is also, because it's an integer, allowed to be negative. So if k was negative 1, you'd be subtracting 2 pi. If it was negative 10, you'd be subtracting 20 pi. So you can imagine that for every value of k, you generate one more answer. And you can keep on putting in k as 1, 2, 3 to infinity, and negative 1, 2, and 3 to infinity. So that generates all the infinite number of solutions there is to that particular trig situation. Now this one looks a little bit different, because it's the first one we've met that has a sine and a cosine in it. And that might throw you a little bit, but I'm going to do a trick that we're allowed to. As long as you divide both sides by the same thing, you should be able to get away with it. So let's divide both sides by cosine theta. And now what happened here? Oh, that's going to become 3. And this guy here is going to become a tangent. So root 3 tangent theta. That's cool. And this fella here, they cancel out, you're going to get 3. Imagine what's going to happen next is I'm going to divide both sides by root 3. And I'm just going to tidy that up a little bit. It ends up being root 3 when you do that. And now I can move on to the final stage. Who are the angles that works for? Well, the tangents are always a bit messier, because you're not looking for an x coordinate that's equal to root 3. You're not even really looking for a y coordinate that equals root 3. What you're looking for is a coordinate. When you divide the y and x coordinates together, you get root 3. And it is positive, and that makes it a tangent is positive in the first quadrant, which ends up being that one, and in the third quadrant, which ends up being that one. So we are looking for the first and third quadrants. There we go. Well, all we need to do now is generalise it. Okay, well, a little bit different than the sine and cosine. The period of the tan function is pi. That means it repeats itself after pi radians. So you don't need to go all the way to 2 pi before it repeats. It repeats itself after pi. Well, the general formula is the unique solution you've got plus the period times k. So pi over 3, right, plus pi k. Nothing wrong with that. Now if you take that, you then get the other guy. But there is a little problem here. If you look at all the solutions that you get from here, do you know they're already inside here? As soon as I fix this one, there we go. So what would happen quickly correcting these to the right values. So what would happen then if you took an example, this fella here? Well, if you add pi, you get pi upon 3 plus pi, which is 4/3 pi. And all the other ones have that same feature. So all the solutions to that second group are actually contained inside the first group. So you can just use this fella as your general solution to all of them. And that's us.